Hi, I will be doing a workshop today on how to use a software called KiCad. KiCad is a printed circuit board design software similar to Eagle. That's open source, so anybody can use it. And it's an easy way to both make a schematic for a circuit and build the PCB that you'll be using for the your design. So first, I thought I'd show what our finished schematic will look like for today. I did a very basic circuit. It's basically the Atmega chip, Atmega 328P, which is the computer, the microcontroller that's used on the Arduino for like the Uno and the Nano, etc. The USB to UART, which is basically the way that the Arduino communicates through the USB, along with the USB port, and a simple button and LED. So let's start with a blank. So if we go to recent workshop, we have a blank schematic now. So we know we want to make use the Atmega 328P chip. So up here there's this place symbol button that you can use to basically look for all of the parts you're going to be using. So it loads the libraries, and then once it loads we can just look for Atmega, scroll down to 328P AU. We have it right here. So now we have this. Okay, next. Before we go into this, I thought I'd go over briefly some basic electrical engineering properties. So if we go to here, we basically have a example of what voltage, current, and resistance is like. So they compare the voltage, current, resistance in this diagram to basically the current being the flow of water, the voltage being the pressure being applied onto the water, and the resistance being the size of the tube. So this is an easier way to basically think of how these values are looked at. So, and then we can look at the Ohms Law, which is basically a way of determining the different properties. So we can see that voltage is equal to the current times the resistance, and you can basically manipulate this equation to whoever you're trying to find. And if we go back to this schematic, we have this Atmega chip, but we don't really know what to do with it yet. But we can basically, if we want to do a basic, find a basic way to do it, we can just look up Arduino Nano schematic. We do this, we see that it shows a basic schematic. So I have one already up right here. This is just a small schematic edit for it, and it basically shows the connections that have been made. And we see that for VCC, which is power, that's how they call it, it's just connected to a VCC pin. So let's do that. So if we see here, we have these two VCC pins at the top, and over here there's this thing called a global tag, which is basically a label that allows us to connect parts without having to do wires crossing everywhere. It's basically a way to keep your schematic clean. So let's call this VCC. So here we have this, and you just do a connection. There's this wire here, or you can just press W. So let's do a wire connecting to here. And let's go back to our schematic. So now we see that this A ground, ground, and ground all connect to ground. So let's make one of those. If we see right here, we see this ground or power port option. So we click, and it basically brings up this menu. You scroll to power and scroll down, you can find a ground pin. So let's take one of those, and we see ground down here. So let's just connect this. And then AREF also over here, which is that other ground. So let's take one of these again. Basically connect. Okay. A-ref actually connects through a capacitor. So we see A-ref right here connected through a capacitor. So let's add a capacitor. So if we go to this place symbol again, we can just look up C. So this capacitor is basically just one of the parts that you're going to use for electrical engineering. So there's resistors, capacitors, inductors. This one will only be using resistors and capacitors. So let's just put one of these in. And we see this has 0.1 UF. So let's change the value for this capacitor. So we click on the C. We can just click on here. It brings up this value. And then we can just change this to 0.1 UF. Now we have that. Let's go back. So right here, this is an external clock. So at Mega Chip, when we look at the datasheet briefly, comes both with an internal and external clock. The internal one works, so you don't have to do this external clock, but when you're going for more precise measurements for clock, so like if you're using the timer function for Arduino, you might want to use an external clock. But for what we're doing today, we won't need it. So then let's go to what do we want to build. So as we saw before, it's an LED and a button. So let's first add an LED. So we're probably looking at these and thinking, what do these mean at all? But there's a picture that you can look up which basically does a nice comparison between the Arduino and the Mega Chip, which is seen right here. So we see that the PD 0 through 7 are these 0 through 7 pins. The PC pins are all the analog pins. We won't need that for today. And so let's do PD3, just pin 3. We can use an LED. So if we go to symbol, let's find an LED. So LED, we just see the simple one pop up. So we can place this here. And for LEDs, you connect one side to power and one side to ground. So let's do a ground. Okay, so we have this, but we should remember current. So as we mentioned before, current is the flow of water or flow of electricity. And we want to limit the amount of current that's going into this LED or else it will blow. That's where you use a resistor for, to add the resistance. So let's add a resistor between this LED and the power pin. So R for resistor. There we go. Okay. And we have this connected to PD3. But we don't know what value we want to use for this resistor yet, so we got to find that. So let's start by basically looking for LEDs. So the site that I usually use for looking for parts is DigiKey. It's one of the biggest electronics parts suppliers. And let's look up LED. Okay, so we see this top results. We can go into here. And we basically see all these options and all the possible parts. So going through here, most of these you won't need, but let's say you wanted to decide the color, and let's say you wanted a red LED. We can just change this to red and apply that filter. So now we're only looking at red LEDs. Okay, so we still have which one, trying to decide which one we want to do. So these numbers right here are basically the sizes of the LED. So they're in imperial units. So to convert it to metric, these, for example, 0805s, they're 2 millimeters by 1 millimeter. It's pretty small. For soldering, we're doing all SMD parts. If we want to look at a comparison for through hole versus SMD, we can basically see this. So SMD parts are smaller, and they're a bit harder to solder. And so we want to keep them large enough that we as a student can still solder them. So in my experience, for soldering, you don't want to do anything smaller than 0805 because it's just too difficult, and you either have to pay someone to do it or you have to get it done by a company. So let's do this one. So if we click here, we come to this part, we see it, and we see that there's this thing called a forward voltage. What this forward voltage is that when you're calculating the current going into the resistor, you basically subtract that from the source voltage and divide it by the resistance that you're putting. And then this, for most LEDs, the current that you want going through it is between 20 and 30. So let's pick 10, for example. So it's safe enough that we can fully light the bulb, but there's no chance of it blowing. So if we go back to here, so for both the Arduino, Uno at least, and what we'll be doing, we'll be using 5 volts as the source voltage. We haven't decided, we haven't put where the source voltage is going to be coming from yet, but we know it's 5. So we have 5 and 1.8 coming from the forward voltage here, and we're trying to find a resistance that gives us 0.1 amps. Okay, so let's do the math for this. So we know that current is voltage over resistance, which means that the resistance will be the voltage over current. So let's do the 5 minus 1.8, and let's just divide it by the 0.01, excuse me. We get 320 ohms, which is what the resistance is measured in. So 320 is it's not a standard value. So there are usually standard values that resistors are found in, such as like 220, 100, 330. So in this case, we're just going to do 330 ohms. It will be slightly less, but it should be fine. So let's change this resistor to 330. Okay, so now we have an LED. We still need a button though. So in this case, I'm going to be showing how to do a button that might not be in the symbol library. So like, let's say you found an exact button, but it's different from most of the buttons that you'd find here. So I'm going to show you how to find it. So let's say and add it to the library. So let's say we look for a button. We go to this tactile switches, and we get all these buttons. So let's say we have this one here. It looks easy enough to solder with the pins coming off, and but it might be of a different size than the ones that are in the library. So what we can do to find these is, I use a site called SnapEda. It basically allows you to find symbols and footprints for parts that might not be in KiCad. So like, let's look for this part. So B3FS-1000P. B3FS-1000P. So we see it, but it doesn't have a symbol or a footprint. That's okay though. Let's try to create a more vague part search. So B3FS, it's still buttons, but it's going to be allow you to look at different versions. So we find this B3FS-1010P, which has a footprint and a symbol. Not the one that we're originally looking for, but one that does still work. So let's just make sure that that's available. So let's type that in, B3FS-1010P. Okay, and we see it is available. It's a bit more expensive, but we have a part for it, so that might be one that we want to pick, or for that reason. Okay, so we have this part. Let's click on it. You do have to make you do have to sign up in order to download symbols and footprints, but it's all you do is sign up and that's it. So we see this part, and we see that there's 4 points on here, but there's only 2 here. So that's because if we look at the part, the datasheet for this, if we scroll down to the bottom, we see that the top pins are connected and the bottom pins are connected. And they show this in here by having these two pins light up, and these two pins light up, showing that these two are connected. Okay, so let's download these. So we have this KiCad pre-V4. Download it. It should give us, so I have to sign in. This is taking a moment. Long moment. Okay, so let's just look that up one more time. Okay, so we have this part, and let's download it. So we pre-V4 KiCad. KiCad is the software we're using, and we basically get this zip file with two files inside. So if we go to here, we see this lib and mod file. So lib is basically the schematic file, so it's what we see in here, and the mod is basically what we'll see when we move over to the printed circuit board layout, which will be later. So I like to put them in separate folders, but for this we'll take them both and move them to a folder together. So I have this HighTechU folder already ready. I have them downloaded, but we can replace them. So replace. So now we have these two library and mod files. Okay, but we have them in our folder that we want, but we don't have them added to KiCad yet. So I'll show you how to do that. So we're going to go to this Manage Symbol Libraries, and you see all these part libraries that we were loading up before, and you can add one that you have basically by pressing this Add Existing Library to Table. So we basically just go to where our library file is, and we just add it. And we see it shows up at the bottom now. So we have the library file in, but we still need to add the mod file. So that's where this footprint editor comes in. Footprint editor is basically what's going to be showing up in the circuit board layout. You can make parts as well, but we won't be doing that as it's very time consuming. I wouldn't recommend it unless you're doing this maybe for a job and you're really into making sure that everything is precisely correct. But to add a part, we go to the Manage Footprint Libraries. Same thing. We see the same setup, and we just add library. So it looks different, but we can just see the mod files right here. We add it, and it shows up at the bottom, like this. Okay, so now we have both these parts in. So now, if we go to the symbol thing, and we're trying to add the button, we can just look it up, and it shows up. There we go. Okay, so let's add this to a pin as well. So we can just put this right here. And let's, so for the button, we know that we want to be able to turn it high to show that it's on, and we need it connected to the Arduino, or the Atmega chip. So let's connect one button to the Atmega chip. We can do PD6, so pin 6. And the other side to VCC, which will be our high. So let's just do VCC. Connect a wire, but there's something we should remember. So there's a concept for resistors called pull-down resistors. What these basically are is that the goal of checking for this input is that it's at 0 normally, and then it's pulled to 5 volts when this button's being pressed. But when we currently have it, how we currently have it, this value that's going into the button or to the input when the button's not pressed is undefined, which doesn't always have to be a problem, but it's not good to leave it like that. So what we do is we add something called a pull-down resistor. So this resistor, we basically add it as a resistor going to ground connected to the side that's connected to the button. So we can add this here and add a ground. So what this does is that when the button is not being pressed, the voltage at this point, the value, will be automatically 0. And then we have to set the resistor value. So in the cases like this, what you do is you set it to a very high value, something like 10k ohms, because what you want is that when the button's being pressed, the current going through here is very small, so you're not wasting much power. Okay, so we have this button and we have this LED, but we're still not done. So we want to be able to program it. Currently we can't program it, so we have to use this chip called a FT232RL, which is this serial to UART communicator, USB to UART. So let's add that, so that will be in the library. So let's place a symbol. You can find it, 232RL. Here it is right here. So let's put this over here. And then we also want, it's going to be communicating through a USB port, so let's add that. So we go to here, we can type in USB. We can see this USB micro, and let's use this. Okay. So now we see this D plus and D minus. What these are basically coming from the USB are shifted sine waves that are basically used to communicate information. And this is then converted to information that the Atmega chip can understand. So in order to understand how to use this, let's go to the datasheet. So I have one set up here, and we see this USB powered configuration. We see pin 2 of the USB port connects to to this USB D minus, and pin 3 connects to D plus. Same thing here. Pin 2 connects to D minus, D plus connects to D plus. So let's add a connection for that. So we can just do a wire between the two. So we have these grounds. Ground just connects to ground. Shield goes with it. And then the last thing we have is this Vbus pin. So this Vbus pin is basically the power coming from the USB. For standard USB, it's 5 volts. If we go here, we see that it's connected through something called a ferrite bead. So this ferrite bead is basically a way to limit the noise coming from the power line due to the noise that usually comes through whatever the USB is connected to. So we can look for that. We can place that. So ferrite, you see it right here. Let's connect that, and that connects to VCC, which also connects to VCC-IO. Okay, so Vbus. So this connects to VCC and VCC-IO. Okay, so the idea behind here, we see this VCC thing right here, which is different from this, is basically saying this is where we're getting our power. So let's add our VCC tag to show that the power is going to be coming from the USB. That is added. So we do need a filter capacitor. So we see here that there's this VCC and there's these two capacitors here. We have a 100 nanofarad and a 4.7 UF capacitor, and these basically connect to the VCC here and to ground as filters. We also have a 100 nanofarad here. So let's add those. Those are also just to limit noise on the power line. So we have these capacitors. Copy this. Yes. One moment. Yes, so as I was mentioning, the filter capacitor is basically a capacitor you put between power and ground. and it basically acts as a way to limit the noise coming on the power line. And so you usually add it for all pieces. So we're going to be adding one over here. We can see that in the Arduino schematic. It shows up right here. So we see this VCC to ground. And it shows up in our USB to UART configurator. We see this VCC to ground. And so we will be adding capacitors for that. So we have these two capacitors right here, which are basically going to be used for the filter capacitors. Okay, so let's add that. We have VCC. We connect it from the tops, and then we can add a ground. And let's change the values to what they have here. So they have 100 nanofarads, which is 0.1 UF, and 4.7. Let's add that. 100, 0.1 UF, and 4.7 UF. Okay, we also have to add all these things to ground. So let's do that.